Sorry about the delay. I'm very pleased to introduce Cristiano Ceccato, who holds both a diploma from the AA and a master's in computer science from Imperial College. After qualifying from the AA Diploma 11, he worked with John Fraser in Hong Kong. He then went to Los Angeles and Frank Gehry, and he provides technical expertise worldwide as Gehry Director of Research and Consulting. He's thus uniquely qualified to integrate the most advanced computing techniques into the most advanced architectural form-creating processes. Thank you. Chris.
So, good evening. It's kind of one of those things when you're a student here. I've sat where you're sitting for so many years, and actually to be here is kind of a bit nerve-wracking. So there's that to think about. I've done 2 red-eye flights in a row, and as you probably heard, the lecture got delayed because I was actually locked inside a house because the guy I'm staying with locked me in, and we had to get a guy to let me. It was crazy. I can't actually believe I'm here. So anyway, but we are. So it's been a while in the making, and it's nice to be back here after a while. The work that we're going to look at this evening is, I really want to sort of talk about different aspects of sort of architecture and process. And obviously there's a technological component about how you facilitate some of these. Suffice to say that I work as an architect in Frank Gehry's office. We have also a kind of technological spin-off company that consults also within our office and to other people to provide certain tools and methods of work across different projects. So the tools really remain a mean to an end, and the way that you sort of engage these tools, use them, modify them, otherwise apply them, remains something that you have to do with sort of a critical eye. So it does not detract from your existence as an architect. Perhaps it enhances it. I don't know if you want to actually turn off the lights or something in the front so you can see the slides better, because some of them are a bit dark, you know. So brilliant, thank you. Some of the work you see here, I think, in many ways has evolved from all the way back from my student days. When I was a student here, I was in fact a student of John and Julia Fraser, and a lot of that sort of thinking permeates the work we do today. And the way that technology has caught up with that sort of way of thinking allows it actually to sort of really come into its own. I sort of want to lay out 2 sort of basic themes of discussion, or sort of underlying subliminal themes that sort of pop up from time to time through the talk in a more implicit way rather than an explicit scenario. One is sort of a topic, if you like, of searching and of finding at the same time. The word emergence comes to mind. It's a dangerous word. Everybody uses that now. This thing is emerging from a system or something. This is really about actually the nitty-gritty pain of actually getting a design, a final design, to emerge from the ether of all possible solutions. There is inspiration, of course, from nature. Nature's been a great inspiration, particularly the application of natural systems of growth, of aggregation, and of somehow spontaneous form aggregation, whether you have them in schools of fishes, or whether you replay that in sort of looking at architecture and form generation as an artificial life form. In this case, the idea of breeding types of design and actually interacting with the computer as a kind of as an actual design partner, as a muse, is something that maybe we're all kind of used to, but in fact actually being able to engage the technology so that it really does for you what you're looking for, rather than kind of only being subject to sort of a particular output of a particular software, is something, again, that you have to do with quite a critical eye. So here the idea is obviously that you can sort of embed knowledge in a system that provides, you know, wide array of solutions such as these, where you can perhaps breed different shapes using natural sort of selection algorithms and genetics and so on. That work sort of began a while back at the AA with John, who is one of the pioneers of this way of working. And the idea there was really to sort of abstract a series of natural hierarchical processes that would look at the ability to engage form generation as a sort of a product of a process rather than a simple artifact. And thereby, actually, by controlling an artificial growth system, an environment, and so on, you would actually be able to look at how do you, by tweaking the process, control the actual outcome, which in this case is some sort of shape. This shape down here is sort of the output of a growth-like process of multicellular kind of artificial organisms. And the interesting thing thereby is not just the final shape, but is actually the system that is used to create it. If you apply it to sort of urban context and think about, well, what about the real world? Then obviously you have a situation that is more pertaining to the laws of economics. If you do economic research, and I'm not an economist, but I worked with some at the London School of Economics, it does tell you that there are very, very specific, very clear rules in the bottom-up dimension, i.e. in microeconomics, that explain the laws of supply and demand, return, and so on, that actually map themselves across multiple scales of activity to generate these sort of, again, dare I say it, emergent patterns, which is basically the field of macroeconomics. And macroeconomics looks at the emergence of patterns and of behavior, and of course the relationships across multiple scales of operation, and in particularly, what about if you have related or interconnected economic systems that generate form? In this case, we looked at the idea of evolving economic rules across networks of simulated cities that were basically populated by data derived from the big information bank that exists at the LSE. The LSE is a really, really good resource, by the way, if you're into this kind of work. And they're just dying for people to actually come in and sort of apply it and do something with it. In this case, these sort of, I don't think we have a laser pointer, maybe we do. Aha. So these things here are, if you like, these hexadecimal code scripts that were seen as sort of an abstraction of, if you like, policy rules that would be exchanged across the network. This is the mid-90s, so the technology wasn't very good, but basically would interact and allow these things to evolve in different ways. The idea here is, of course, is how can you capture the effect if you have something like a crisis or a stock market crash in Tokyo, how does that manifest itself somewhere else, like New York? And applying different rules is a collection of results. It became sort of like the story of my life later, because I used to live in Hong Kong for a while, and then I now live in LA, which kind of looks like that. The idea here is that you're not actually calling this literally a design, but this is basically a form of three-dimensional emergence as a byproduct of economic activity. And the interesting thing there is that it is really governed by these laws of economics and micro and macroeconomics. And basically you're trying to influence that system, and it gives you a sort of understanding what a potential outcome might be. The application of that happens then at the large scale. This is from 2000. We worked on some competitions as a team out of Hong Kong, working with Arup and working with a few other fellow architects there, where we looked at some of these urban planning designs. And there, of course, the scale is enormous. You are asked to design a city for 200,000 people, and you have very little time to do it. And the question is, how do you, on one hand, lay out the sort of overall location of things, and then how do you also then diversify what you're putting down? Normally what will happen in China is that they will design one tower, and it's probably a very dumb block, and maybe it's sort of 25 times the same floor plate extruded upwards, and then they will sort of copy it, I don't know, 200 times, and your project is kind of done. And that, of course, makes for very, very bad urbanism, and that's a whole different lecture, and we won't get into that. Suffice to say that the layout of these buildings and then the design of the individual pieces, we started to explore, saying, can we actually find aggregations of perhaps similar or self-similar components that can perhaps speak to some sort of industrialized or semi-industrialized process that could actually bring some sort of variance into a project like this. Other things that go on in the background are this kind of stuff. This is some collaboration with a friend and colleague of mine. You obviously know the project on the right, which looks like making of bubbles by PTW. And the work that he's doing is looking at sort of the rationalization of bubble structures, in the sense of that, can you actually find common components if you wanted to build something like this? And, sorry, the slides got misaligned there. Okay, so let me just fix that. This is part of the, while I do that, I just wanted to let you know that I was actually kind of finishing laying these things out when we were actually sitting in the car driving here after they broke into the house I'm staying, and it was pretty crazy. It was also pretty expensive, you know, to get yourself broken out of a house like that. It's like a lot of money. So anyway, and sort of the work that goes behind that. I mean, I'm not a bubbleologist. There's this whole science of that about how water and, you know, soap bubbles aggregate. But there's actually a very, very clear set of mathematical and geometric rules about the relationships of geometry that exist between the individual bubble-like components, particularly if you have intersection of spheres of different dimensions. And so there's a whole inane amount of mathematics that goes behind this, and I won't really go into that. Suffice to say that there are very clear, distinct relationships between these different intersecting spheres. And if you can actually capture that as a sort of a modus operandi, you can actually begin to develop a flexible design system that can actually produce sort of different kind of bubble aggregation structures where you can make sort of modifications to perhaps a parametric system that allows you to lay these things out and actually control the types of components that you are going to generate. Another area of interest before we get to the project is the idea of search. And in this particular case, it's about the search of the unknown, which is sort of a paradox. But if you Google something and you put in a name and you say, I want to find, I don't know, all the pictures of Angelina Jolie or something like that, you can find them. But what about if you're looking for a shape? I mean, I can say Google blob and I'll get something. But if you want to describe a shape, it's much, much difficult. This is from some research that's going on at Princeton, where they've actually developed a three-dimensional search engine where you describe not by words, but by doing small strokes in a little Java applet to describe kind of what you're looking for. And it tries to find and match patterns of form where the form is unknown. And of course, there's tools that are sort of, you know, these so-called parametric software tools where you have to describe relationships and that sort of thing. But what about if those relationships are unknown? How do you actually distill what the relationship of forms might be? So, you know, in some cases you can do it with things like this composition of spheres, or something that interests me a lot is sort of the idea of skeletal graphs, where you have really completely unstructured information. This looks like an airplane to all of us, but the computer doesn't know. It's just a bunch of triangles literally flying in close formation. How do you find out that that really is an airplane when you have no structuring of information? And if you can do that, then obviously you can sort of reverse engineer a kind of a graph of how these things put together. Now, why is that important? The reason that it's important is when you actually have to design with this stuff, if you use a tool like CATIA, which is very good for certain things, but very bad for others, you're actually limiting to shoehorning yourself into what that graph wants you to do. And if you don't have such a thing and you want to infer it later on, it actually frees you up to be much more, if you like, spontaneous about the kind of work that you're looking for. So really pushing the way that the computer is interacting with the design and really being responsible to maintain the computer being a means to an end and not becoming the driving force all the time, but actually having a symbiotic relationship between the design team and the computer itself is what really makes the computer actually come into its own. And that's sort of, if you like, the distillation of the 4.5, 5 years I've been spending in Frank's office. When you then actually go back to doing design computation, you start sort of looking at emergent form and doing all kind of algorithmic forward generation, you really do start thinking about, well, what does it mean when you have sort of spontaneous cavities emerging and so on as a design? And you also think about how can you describe that in terms of, you know, its actual makeup. A blob of some form is just a blob, but can you actually find a blobological descriptive language of some form? And so if you can actually surmise or extract the internal sort of features that make up such a thing, it becomes actually something much more easy to control. Werner Heisenberg is a very interesting figure. For those of you who don't know him, he won the Nobel Prize in 1932. He produced a theorem called the principle of uncertainty, in which he stated something like, along the lines of that if you look at a discrete atomic system, you cannot actually calculate with infinite precision the exact position of an electron in that system because the electron moves at a speed that you can actually quantify. So what does that mean? It means that the unpredictability, the imprecision, is actually built into the system itself. And that's actually quite profound because we try with the computer to be very, very precise. You look at a 3D model, drawings, everything, you know, really lines up. If you did some, you know, those of you who have drafted in AutoCAD, you know, do the lines really match up and look really clean? And then you go on site and you find that actually nothing fits because, of course, you're dealing with the problem of tolerance, and we'll get to that later. So that particular issue, if you sort of take that uncertainty principle and map it upstream to design, you get this sort of situation. This is not actually a Gehry project. It's by a different architect whom I worked with for a while, where this is basically a temple in South America for the Baha'i religion. Very, very interesting kind of ecumenical sort of religion. And one thing that is a typical thing about them is that they have this sort of, these 9-pointed kind of dome shapes. In this case, he's come up with this sort of flower. And he sort of designed this brown structure you see underneath here. And that was designed in Maya. And basically, as you know, Maya works with subdivision surfaces, and it tessellates sort of submerged patches to achieve a certain curvature and solve sort of curvature discontinuity problems. The problem is, how do you build that? And when you work with Frank, you know, for me, I was a student here many years, and also I spent some more time doing more research. I wanted to spend some time understanding what it means to build really, really complex forms with really, really advanced tools. And that's sort of, you know, the actual design in Frank's office is something I think I sort of came to appreciate after a while you're there. You can see the nuances of what he's trying to do. But it's really the method of actually executing pretty much anything that Frank throws at you that becomes sort of the dexterity of how you deal with this stuff. So in this particular case, it was, how do you build this thing? And whether you sort of, if you goop it out of Bondo, or you sort of plaster it, or you make it out of concrete, then yes, you could sort of make a big sort of free-form leaf like that. In this case, the architect wanted to build it out of a series of plates of stone, and there was a budget limitation here in which the stones actually could not be milled, double-curved, whatever stones. They actually had to be from a stone block that would be cut up in regular stone slices and possibly at least form two particular quadrangular forms. So the question is here, you need to rationalize this brown shape into this blue surface that you see lying over. You see it's got lots of facets. And then on top of it, we've actually laid the final milled, chamfered, detailed stone pattern here as an example. And so the question arises, where is the actual design? Right? Is the design the brown thing? Is it the blue thing? Is it this sort of weird intersection in between? Is it the final stones? Is it the final stones on site that the contractor breaks a few and has to goop them together, and that's the final thing? You know, you go to the Liebeskind Jewish Museum in Berlin, which is a really nice building, and you know it does this blitz zigzag through the landscape. And you go inside the building, and one of the things that's exhibited inside, there's the final design model of that very same project. And if you look at the design model, it's actually quite different. As it zigzags along, the walls become more and more and more tilted as it zigzags along. And the question is, why was that design with the zigzagging tilted walls? Why did everything become straight on the field? That is a very big problem. I mean, whether, you know, did they run out of money? Did they not foresee this problem? The contractor didn't know. The client didn't want the risk. There was some problem, obviously, that meant that these crooked walls became straight. And the question then is, not only where is the real design? Is it that little model sitting in this shed that looks like it? Or is it actually still somewhere in your mind's eye, and you're just trying to find a way of rendering it? So that you could argue that the finished building is basically a rendering of the actual initial idea, just another view of it. It's just a one-to-one giant rapid prototype, maybe. So in the case of our office, this is a shot of our old office. We've since sort of moved to a bigger place. Some of you may have been there. This is Craig Webb. He's one of the two design partners. He's standing there in a bunch of physical models, and he's contemplating a physical model. Lots of computer screens secretly hovering in the background. It's kind of nice because they're all sort of semi-plastered in with glue and paint, and it's all very sort of touchy-feely, and they're just running expensive software. But what is interesting is that you see these collection of these sort of design objects up here, and they are all sort of an evolution of these ideas, trying to kind of find what it really is that you are looking for. And the physical making of models is one way of trying to find a form. It doesn't mean that you're literally going to build it out of strips. It means that you're trying to, in this case, approximate a design idea that works with some sort of spatial programming underneath. You could be doing this with a NURBS surface in the computer. Frank really likes to do it physically because he can go in there and start chopping it up. And, you know, everybody has his own way of working. Suffice to say, this is a shape. It's not a building. That shape now begins to get digitized. We use these sort of reverse kinematics transducer arms, like a microscribe here or a larger ferro arm. And what happens when you do that is you're sort of recording specific points along these curves. And already now, you already have a problem, because when you're touching this thing, it's a very tiny pointed microscribe, it's very, very precise. You're actually making very, very small indentations into this paper. Maybe your hand is trembling a little bit, and because we are in Los Angeles, you might have an earthquake, so everything wobbles. You know, you get funny little tremors, and it sort of jiggles, and you know, it's just part of the day-to-day. When that happens, you have to throw it away and start again with a dig, because, you know. But anyway, there is already some variance going on just through the digitizing. This then comes in, you have to place some curves or surfaces over that, and maybe Frank really is looking for that little crease or crookedness that means something within the design. That gets lost maybe because obviously what a NURB system tries to do is actually smooth out between interpolating points, if you look at the mathematics of it. And so maybe you're saying, well, the computer's actually trying too hard to help me. So when you're actually kind of bringing in these shapes and then you're going the next step down, this is from another project that I'll go into in more detail in a little bit. And at that point, you're now talking about the blue thing being, the dark blue, being some sort of idealized shape, and trying to find a buildable solution, not unlike the project I showed you before, that has to somehow approximate that shape. The question is, could you design directly with that system? Yes, you could. But then there's, of course, that kind of dialogue about, you know, which comes first. Is it just sort of the conceptual design, or do you really actually want to immediately sort of, you know, we have a lot of interaction with Foster and Partners. We've done some competitions actually together, believe it or not. And it's interesting when you work with somebody like Hugh Whitehead that there really is a different approach in the thinking. I mean, everybody's very good at wielding tools, but what does it mean to find the shape? So the bottom line of this whole description really is that on the one hand, the left-hand side, you have some sort of emergent shape emerging out of a process, whatever that process may be. In this case, it could be a computational form-finding process. It can be an evolutionary process, design process. We can talk about that. And on the right-hand side, you actually have a construction. And just because you know how to do this and it kind of looks like a truss doesn't mean that it actually will get built. The inequality sign is very, very big. And that's kind of been what I have learned, personally, I can say, over the past few years, is really what does it mean to remove that inequality and make it an equal sign? That what you are producing at the design level really does translate into an actually constructible edifice that matches all the criteria of a particular project framework that goes everywhere from, of course, the budget and the timetable to what the client is really, not just what he's looking for, but what kind of risk he's really willing to incur. And that's, client risk is like number one problem in all of these things. Right down to what can the actual fabricator do, you know, will he get stuck, and so on. Another example is, sort of, it's on a similar line, you're sort of getting the theme now, is Michelangelo, the Pietà Rondanini. Interesting, I was going to say project, but that would be a lapse. It's more like an interesting sculpture, I guess, in this case, because Michelangelo passed away before he could complete it. So what you're looking at is really work in progress. And you can see the legs here are finished. He's actually got a fully finished and polished arm that he's sort of abandoned, and he's now kind of gone off the other way. If you look close up, you'll see the Madonna. The lighting's not good here, but the Madonna actually has two faces. So he's still deciding, is she going to look this way or at that way? And there's something, again, being drawn out of that stone block that to him is somehow in there. And he's sort of almost just kind of removing, chipping away at the stone and kind of letting this thing come out. And I think sort of the interesting thing about that is that in a way, when you go through projects like this, they begin to take on a life of their own. And there's so many factors that guide a project that at some point it becomes, on one hand, it converges on a solution. On the other hand, if you're trying to steer it down a particular path, it becomes harder and harder to keep it on that path. So I don't know if you can recognize what this is. It kind of looks like Brancusi, but it's not. I don't know what this is. This is one of the front fan blades of a G90 engine. This very, very big aircraft engine. It's the currently largest engine in the world. Actually, here projected, it's a little bit bigger than life size. They're giant 116-inch fans. And these are sort of when you look in the front of the engine, this is what you see, one of these, kind of looking at it from the side. And if you look at the Rolls-Royce version of this, of the Trent, what's interesting about it is that it really is actually a grown artificial thing. So what that means is that it's made of some sort of secret titanium alloy, but it's not cast, it's not forged, it's not rolled, it's grown. What that means is, if you remember as a kid, they would have you do the experiment where you'd put a piece of string in a glass full of sugar water, and sort of the sugar would begin to clump and the crystal would grow of the sugar. What they do here is that they found a way to control this growth of this crystal as a single crystalline thing. So they can influence it with some sort of secret forces, whether it's electrical or otherwise, pressures, that they can get this thing to grow into this incredible double curved shape, and it's actually a single crystalline object, which means it makes it incredibly strong and incredibly light. So at that point you really can say, wow, this really is a artificially grown thing, right? I mean, it's sort of like almost an artificial crystal. So it's kind of interesting to think about that we as architects get interested and fascinated by all the stuff, and they've been doing this, for quite a while. I think Rolls-Royce won the Queen's Achievement for this in 1989. So I mean, it does exist since a while. The other sort of topic that I wanted to talk about is the idea of mastery. And by mastery in this particular case, I don't mean, I'm just a master designer, but by mastery I mean you have really a mastery of your project. You have that kind of level of control that allows you really to let the project evolve and be designed and executed the way you really want to. And one thing I learned, this year I've been spending a lot of time in China on a lot of projects, and so, you try and learn something about the language, and I'm not very good, but this means construction. It's jianshu. I hope I'm pronouncing it. If somebody Chinese here, don't hate me. Or you can, jianshu. But the funny thing is, in Chinese, if you have the wrong intonation, you can be saying something really offensive by mistake. And so it means construction. And it's sort of the two key characters that basically outline the complete sort of vocabulary for construction. And if you think at architecture, it's, I think, jianshu shiji, right? So it means basically construction design, and that is architecture. The interesting thing is that architect is actually jianshu shi, which means construction master. Not architecture master or design master, it means construction master. And that to me is a really interesting point, because it really means that it sort of harks back to the days of the master builder and of the architect, the overall father of a project that understands the complete construction, is not just sort of the glorified shape maker or the decorator. He's actually really completely empowering and transcending the complete process. And the reason that's interesting is that's one of the things that I think the Gehry office has had to learn to work by, because there's no other way to execute those very, very particular projects, and in particular there's no way to convince your client that you can do them. So sort of iconic image from Kubrick, he with this one he sort of stated that at some point in early man began to find a way to take an inanimate object and turn it into a purposeful artifact, and actually be able, in this case, to take a bone and use it as a mallet to bash open other bones. That particular point in time of becoming a tool maker is something that we as architects actually have to think about, which means that, again, even if you're playing with software, some of you play with scripting or otherwise, think, what does it really mean to try and actively engage yourself into controlling and getting the tools to do what you want to do, and not you just saying, well, I've got mine and it's got XYZ tools and it just does whatever. Because that, in a way, is you're sort of becoming subservient to what a particular tool can do. So how do you put things together? And a simple way is obviously talking about components, blocks. Lego is a good example, as you know. But also when you kind of go further, you have things like kits of model parts. When I was a kid, I used to try and make these, and I'd be terrible at them. There'd be glue everywhere, and they looked horrible. And you always wonder, why can't you make it look like the box? But the idea that's interesting there is that you actually have a preset, predefined breakdown of a design into a finite set of components that are actually quite logical. And the reason that is important is if you look at something like Airbus, and as you may have, if you may recall, last year Airbus was big news because they actually beat Boeing in terms of sales, and living in the States, I can tell you that went down in a thunderstorm. me as a European would sort of, you know. And the reason they were able to do that is because they did smart design, right? I mean, they basically developed a root object, which is this famous A300, out of which they developed a family tree of all possible airliners by taking, squeezing, stretching, adding, removing engines, reconfiguring things out of a single root that suddenly allowed you to address every possible configuration of the design out of a common set of components that could address for every airline what they needed. The right range with the right seats, as you know, is the difference between an airline being profitable and going bust. Again, living in the States at the moment, you know, half of the airlines are in bankruptcy. So being able to produce actual family of things rather than a single object becomes quite a profound sort of idea. If you go to Heathrow, you can sort of, you know, tell 10 different types to the point that they stretch them, they become like a flying pencil. And such as this one, which is still the same root and yet become very, very long. And at some point, you can't stretch it any further until you need so much structure to brace this thing where it becomes uneconomic, it becomes so heavy you can't fly it economically. So you have basically something like a landscape of all possible designs that reach some sort of limit, either economically or functionally or structurally, after which point, if you think of René Thom's catastrophe theory, you have some sort of dialectic jump to a whole new paradigm of design. And that, of course, is the A380 in this particular case, which is this new mega airliner you have been reading about, I assume, which can then be, in turn, become stretched and pushed and pulled to, it'll probably yield a whole new family of flying ocean liners, I suppose. I wonder what it means to sit in the last row of the upper deck and, you know, you'll be deplaning in 2 hours, you know, because it takes you that long to get everybody out. The reason this is kind of important is that it leads me sort of to the next topic, which is the actual idea of aggregation of information. These aircraft are now built off of a single model. These models are more than just a representational model, or they're certainly not a representational model. They really are what you call a digital mock-up, which means a virtual one-to-one representation in the computer of what the thing really is going to be. Each one of these components is modeled as a true solid component. You can use this to machine things. You can look at how the assemblage works, the sequencing, the scheduling, the supply chain, all that sort of thing. Also, you can use it to do all kinds of engineering analyses, structural analysis, component fabrication. Out of one and the same model, you can use it to calculate weight and, of course, the cost. And the great thing about that is that with Airbus, it is similar, or more similar to our industry than, say, Boeing, because actually Airbus is sort of a name tag for an aggregation of about, I think, 10 different companies around Europe. And they work with, you know, with different tolerances, different instruments to produce all their components that are then put together, just like that model was, to form a single large artifact. So you get to the point where you have literally the machine that makes the machine. And in this case, you have these giant, this is like the coolest thing, I found this here, these giant structures that they reside on these giant tracks, right? They curve around. And you can see there's these huge giant things, and they come together like this guy's hands and go, right? And they actually put together the entire thing. And they're so huge, they even have their own offices, like they have a whole office suite, and they ride on rails, and they put the entire thing together, and then they drive apart, and the plane just drives out, right? And it's like incredible. But you can actually have these giant mobile buildings that come together and just kind of lock this whole thing together. And that enables you basically to have these components that come from all over the world and come together. So what does this mean for architects? There is a kind of different versions of this sort of process diagram. In this case, you're really talking about saying, well, all this information really needs to begin to be integrated into a single location. And we call that sort of, we tend to call it a master model, which is basically a three-dimensional database of information that can be more or less complete depending on what the project wants to do. It can be more or less smart based on what you talk about parametrics or other such things. But in particular, what it does to do, allows you to do is aggregate information from the design, actually becomes part of the design process, but at the same time integrates the whole design development engineering process. What that means is that you can actually use this as a platform of communication to collaborate with your engineers, and in particular with your fabricators, early in the design process, so that you're not just designing a what-if scenario of sort of like, you know, I'm going to triangulate this thing, and then I'm going to get sort of 20-meter long shards of glass that nobody can build. You actually want to work with these guys closely to say, what can I build? How should I build it? I'm trying to do this as an architect. You help me. let's find a common language. In this case, it's a technological language to exchange information, to find a solution that will get your building built. And of course, the key here is to get the building built, right? I mean, as an architect, I think that's a lot of our goals here, is to actually see what happens at the end of the project. Does it actually fulfill that ambition? Unfortunately, when you do that, you confront yourself with all the sort of really dumb, mundane stuff. I will admit openly, I'm still trying to finish my part 3. And you're confronting yourself with things like contracts and sort of the different phases and all that thing. And particularly, you have to say, well, how do I interface a whole new way of working that really wants to do away with an artificial sort of disaggregation of components to actually have a kind of a central hub that can exchange information. And that, of course, means you have to tackle the meaning of contract itself. You actually have to look at what does it mean to contractually record information to the point where you can use the three-dimensional model as the primary instrument of contract, not the drawings, not the bill of quantities, not the QS. The 3D model becomes the driver for everything. And I'm happy to say in this country there's actually a committee which is called, it's called the Construction Fabrication something, which is a joint venture between RIBA, the RICS, the QSs, the Institute of Civil Engineers. All these guys got together and said, we have to kind of find a set of standards where this can actually occur. So this is actually beginning to happen in the UK. We're working on a project in the UK where we immediately jumped on that, and it's still slow to evolve, but at least in this country, we're lucky because it actually exists. In the United States, it's complete anathema. When we talk this, they think we're saying gobbledygook and we're smoking weed or something. So if you look at a contractual document like that, it looks something like this. I mean, this is part of it. Basically, it is a descriptor. It is a descriptor of the information, of how it is aggregated, and right down to the very point of where is it located in space. So I'm actually going to say, contractually, the GPS coordinates of the origin of our site are in a particular location. Thou shalt use GPS of this tolerance. When thou shalt look at this model, thou shalt use, version so-and-so, service pack so-and-so. But particularly, you're actually talking about a disaggregation of components where you're stating very, very clearly what each part of the information in the model means. And that varies from project to project based on the type of contract and the type of relationships that you're actually creating between the different participants. If you're working with a design-build contract, it'll be very difficult. Very different than, for example, having a construction management risk type of contract and so on. So in this case, you're actually not just saying what this is. Here's my steel. I can use that for something. Well, then you state that. You can use this steel in this particular issue of the model. Maybe it's a stage F model or whatever. It's not detailed, so you can use it for the calculation of tonnage, for the coordination of the steel beams with the roof above it, but it does not contain details. You can use it only for certain things. Please see also for certain details reference model or drawing so-and-so. When you're doing then the standing seam roof on top of this, maybe this is telling the roofer where the seam pattern needs to go, but the actual design of how you're going to fold the actual seam, maybe that is left to the roofer because he knows what to do. This is taken from a project we have on site right now at Princeton University. There's a new science library there, and it's sort of halfway up basically. And so this is actually the document that describes to people what they have to do, and the general contractor uses this on site. So this is kind of the equivalent of that Airbus model for a building. This is another Frank project. This is the Disney Concert Hall, which you probably know. And besides looking kind of intricate, there's sort of an interesting thing about this particular image, which is one of process. Here you see this blue surface here. It's basically a contractually binding surface that the architect issues along with some sort of panelization pattern, which is not in this image, that says how you break it down by panels. And this basically is something that now needs to get built. So in this particular case, Frank had a specific look he wanted to achieve. With the engineers, there was this very complex steel structure. It looks very complex because it does a lot of bracing for earthquake, and you want the interior wood geometry to be as little affected by the earthquakes as possible, because it's a very, very finely tuned concert hall. They actually tuned the panels acoustically to get the right reverberation time. And so you end up with this black line that you see here. I don't know if you can see this dark blue thing, right? And that's basically a zone. And the zone between the surface, this is it's a NURB surface of some sort, and what it is I'll tell you in a minute. But basically, it's an infinitely thin surface. It doesn't have a structure, and there's sort of a zone between that and the actual steel, which now has to contain, or gives you a space for operating and building a subsystem that supports the whole cladding. So you give that as a kind of microscopic design-build contract to the fabricator, in this case Parametric, who are of course amazing at this, and they came up with sort of the solution collaboratively with the office. And how were they able to do that? The reason is, and again, in most projects you might say when you go to tender, sorry to belabor this sort of mundane tendering stuff, but it does influence the way you work. So just bear with me. When you go to tender, normally you might say, I'm going to give you a specific set of drawings, a bill of quantities, and you're going to shop around who's going to give you the best price for the information that you are handing out. In this case, the senior partner at Gehry that I work with very closely, Jim Glimpf, he works in a different way. He says, look, we're going to issue you a design specification and a performance specification. What that means is we want the design, or rather the solution that you're going to propose, Mr. Fabricator, to perform in a certain way. That means it has to perform structurally, it has to perform economically, meaning to the budget, it has to perform thermally, acoustically, and also obviously it has to perform aesthetically, meaning that it actually has to implement the kind of project that you're trying to do. And that means that the great benefit of that is that it stimulates creativity in a really phenomenal way. The fabricators really, really love it when you do that. If you go to them and say, basically, I'm asking you for advice. I don't just want to know the cheapest thing. I want to know your advice of how you would build this damn thing, you know? And chances are they know it better than you. You go to Parametric and they say, look, I'm working project by famous architect so-and-so, and of course all his details are crap and we had to redesign them anyway. So in the end, why not go to the source and actually work with these people to find a solution? You work beyond that. You think then, what does it mean underneath that? So you get to the famous, you know, sort of discussion about the 15,000 steel members and the 50,000 gusset plates, but more importantly, the actual weaving of different systems together in a complex process. In this case, what it means, for example, in the roof of the hall, we have here these acoustic panels that are basically covering the concert hall below it, and above that we are feeding air from two lateral service towers into the hall from above, and the air gets sucked away from below the seats. Because it's a very precise concert hall, this has to be very quiet. So to maintain airflow, the duct sizes are really, really big. They're sort of like over 1 meter wide, and so that the air can move very slowly and be quiet. What does that mean? That means that when you install this stuff, you have to install it at the same time as you're installing the brace frame structure for the roof of the hall. This is a primary steel. Some of it's turned off here so you can see this stuff. But basically, you can't sort of weave it in afterwards. There's literally no way to get that stuff inside. So it's kind of like baking lasagna. I don't know if any, you know, being the Italian, you know, if any of you cook lasagna, you know, you put a layer of the pasta and the meat and the cheese and more pasta, right? You weave the whole thing together. And that's kind of what you're doing here. You're weaving this bit of the steel, you're placing the ducts, you're closing out the steel, you're doing this whole process so that this can go in at the same time. Also, so that when you place the wooden panels, even though the cladding of the external of the building is still in progress, the internal box of the acoustic chamber can already be thermally and environmentally, shall I say, controlled. So the important thing is that all these things get delivered and they have to fit precisely on the site. There's no room, literally no room for maneuver. You can't fit this thing in here any other way. So if the fabricator of the HVAC system got it on, the guy who folds the sheet metal, then you got a serious problem on site. You're going to have stoppage, you might have to take something apart. So the only way to do this really is to have a fully coordinated model that people abide by. This also helps obviously when you have maybe sub-steel packages that you give out to different steel fabricators and different steel detailers, so that when you then look at the construction process of this, you can say, well, it also is interesting because in a way you design left to right. You know, we're working on the shapes and the overall layout of the building. At some point you will figure out in the design what the steel has to look like to support these shapes. Obviously, maybe in a different design technique, you might say the shapes are self-structurally, they're self-supporting structurally, or they're kind of like a structural digrid, or maybe they are, you know, some sort of structural surface. That's fine. the main thing is that there's still, even there, different trades fabricating to different tolerances. Here you have already a fairly high-grade steel. This is sort of has a 3 to 4 inch tolerance on site, which means that if you imagine there's a center line through the steel can wobble within 3 or 4 inches on either side. And that's already pretty high precision steel. It's pretty expensive steel that you're talking about there. And still, the final cladding has a tolerance of just a few millimeters. So as I said before, in the computer, everything lines up really nicely, really works. But then you go on site and this thing is wobbling about somehow. Again, maybe a few bumps, earthquakes as you're putting it up. And then you have to get this thing to really look like an airplane wing. And the question is, how do you do it if things aren't exactly fitting? And that's where the experience of being an architect comes in, where the best tool in the world isn't going to help you at this point anymore. You have to know that there is a tolerance jump. You have to work that tolerance jump into the detailing, to have variable geometry details that you can survey with lasers to actually register them to the kind of tolerance you want in the final skin on the outside. So that becomes then part of the design in the shop drawings, but that decision isn't made by the computer, it's actually made by you. As you know full well, you can take these models, use them to do all kinds of also engineering analysis, whether it's thermal analysis, structural finite element analysis. This one here is actually research into a very particular difficult joint in concrete. These are all rebars. And the rebar here, you can see here the mesh for the slab. And these are the framing beams in the slabs. And then you've got some sort of column coming down into sort of this diagonally jointed thing. And the only way to work out whether this column really worked was actually to detail the rebar in 3D. So let's talk about surfaces just a little bit. Surfaces are interesting as a kind of design language, as in a design generator, and also particularly as a design descriptor. Here they have to also work as in the design enabler, meaning that you actually want to build these surfaces. This is the central component of Bilbao, the museum in Spain. And what this is showing you is an analysis called Gaussian curvature analysis. Some of you may know what that is. In this case, we're looking at the amount of compound curvature existing across the surface, which is basically the reciprocal of the square root of the two radius of the biggest and smallest circle on a curve, that allows you to calculate, in this case, how much is it curving. We knew in this case from material research, this is going to be clad out in those famous little titanium panels that you know. A titanium panel has enough endemic flexibility. I keep on looking if I have a piece of paper on me, but maybe not. Why, thank you. So, if I take a piece of paper like this, and you probably can't see it, but it's fine, you will know that even if I hold it like this, yes, it'll curve in one direction, like this. But in fact, there's a tiny bit of curving happening also in this direction. There's enough, just about enough floppiness in the material that it's still double curving ever so slightly. So in this case, we knew that you could take the equivalent of a 60-foot sphere, a 20-meter radius sphere, and if you had a sphere that size, you could actually lay one of these titanium panels on it without it basically crinkling. If I try to bend this too much, you know, you get warps and creases and crinkles because the material can't take it up anymore. So you put that into the system and you kind of analyze the surfaces, and wherever it's light blue and green, you know that basically the material will be able to take up just a little bit of warp. And where it becomes dark red or blue, basically the material can't do that anymore, and you would end up with this kind of crease situation. In this case, you now have to decide, well, what can I do? Well, you might say, well, I'm going to make a mold and stamp this out. Of course, that's horrendously expensive and extremely slow, so maybe that's not very good. You might want to try working like a tailor, making smaller pieces that you sort of can stitch together and actually put together. Or maybe you have to think about, is there a way of defining the surface in such a way with a design team that some of this redness literally goes away? So this is where the idea of toolmaker comes in. This is some of the work that we do on the side, besides working on the project, is you basically solving project problems by working as an architect on the projects themselves. In this case, working with a colleague of mine, Dennis. I took his picture and made that into the icon for his thing. Basically, if you design a NURB surface, and in this case it's a mathematically constrained NURB surface, we're basically constraining across a particular polynomial across the so-called knots of the control points, you can actually get this thing to always behave in a single direction of curvature. So if you put that in a parametric system, in this case what I'm doing, basically the same as this. You know, when you take a big sheet of sheet metal down in the workshop and you can go like that, right? And that's what's happening here in the computer. It's basically only moving in one curvature direction, which means I basically have a form of virtual sheet metal at this point. I can take this and I can now wrap this around any shape I want or design with this. At this point, I know that I don't have to worry about that Gaussian curvature analysis anymore, because this is always going to give me single curved sheet metal unfoldable material that I can basically run off a coil, and it comes with a certain cost per square foot or per square meter, and that allows me sort of to define the cost of my building. You can take something and design with it, so something pleated or something like that. It doesn't really matter what the shape is. The point is that this, you know, can be made in a certain way. If you take that discussion further to a high-rise tower, this is a project we're doing in New York, where you're looking at the amount of twistiness you can have in the surfaces of a tower. In this case, it's a project with a very, very tight budget. By very, very tight budget, I mean, you know, somewhere in the range of like $150 a square foot, which is basically nothing. And you want to find out how can you still have some sort of movement in a project like this. Not just by using panels, cladding panels that are maybe mass customized or they're CNC milled, you know, we can all make them, you know, there's lots of projects where the panels all look a little similar. In this case, you want to make them identical, meaning that you're really going to take a unitized curtain wall system and try to warp wrap it around a curvy surface. And the question is, how do you do that? And to do that, you have to work with a cladding designer to actually look at what are the implications of taking, say, identical panels. So I raided my wife's CD collection, and she makes film, so I stole her gaffer tape and wove this stuff together. We put it onto pins, and you find actually as you move this stuff around, you can actually achieve double curved surfaces. And the point is that the slack is taken up in these gaskets. It's very much like a concertina that you have between the train carriages, you know? The train carriage is a straight thing, and the concertina takes up that thing. So at that point, everything is about that little concertina joint. How much distortion can there be? How much warping can there be unless I have some sort of waterlogging, or I have some sort of, or the fabricator will say, if you do that more than 3 degrees, I'm not going to guarantee that it's going to age properly, and your rubber might break away. So you take those parameters and you put them into a system, and this is like in an artificial intelligence system, which allows you now to sort of tweak that surface behind it. These are now absolutely identical panels, instantiated many times, and you're measuring their kind of artificial intelligence mechanism, these conditions between them. And if I start designing with this, and I start going wibbly wobbly, and these guys move around, at some point maybe one of these conditions will fail, right? And it'll become more than 3 degrees. At that point, this will become red, and the system will go like, you know, wrong. Can't do that. Either you need a different detail, or you need to retweak your surface, or something like that. At least, again, you are kind of undergoing an informed form of design, but not design development, but actually at the design phase. We really wanted to know what kind of shapes can we achieve if we're going to work with a construction system like this from the very beginning. This is a project that I did a few years back in Berlin. And it was a building that was an early modernist building from 1908. It was the first steel frame structure in Berlin. And the project is in the middle of Berlin. This is the Friedrichstrasse and the Leipziger Strasse. It's right on the corner. And the building was severely damaged during the war. And the roof had caved in. The facade was historically reconstructed. It's a stone load-bearing facade that's sort of attached to the steel and concrete frame, which in 1908 was a pretty new thing. Sort of a department store. And it was in East Germany. It was sort of left to rot. It was patched up. You know, a lot of buildings were in East Germany. And the clients who bought it after the fall of the wall, they spent a long time thinking what they wanted to do with this. And sort of in around 99, seems so long ago, they said, well, we want to work out what we could do inside. And one thing I want to talk about really is specifically a staircase system. And you can see sort of looks like Piranesi, you know, you can see just like the state of the stairs. It's sort of absolutely destroyed. It really is kind of like sort of an archaeological place. And as you know, with these kind of projects, you know, there's one I think happening on Rosebery Avenue where they put this giant jig that holds up the facade, and they knock down the building and build a whole new building behind it. In this case, it was a choice that the client had to make, and he decided might be cheaper just to sort of patch up whatever's left. And in the end, of course, it wasn't, but that was his choice. And so we really need to figure out what to do with all this, crumbling stuff. And in the case of a staircase, it's a simple idea of what a parametric construction might be. Normally what you do is you get a stair contractor who would come in, measure it on site, and actually, sort of like a tailor, measure your whole body, in this case measure the condition here, and custom make the entire staircase components and come and sort of custom install every piece and get your stairs right. In this particular case, because of all the patching, they had to pour an additional topping slab to stabilize the floor and do all kinds of stuff, where you ended up with different floor-to-floor heights. And I said, well, that's a bit boring. I mean, what about if we tried to look at an idea of common components that can address many different geometric conditions? So this is sort of early 3D modeling, kind of like AutoCAD style, very, very painful stuff, never to be attempted again. In this case, we are looking at, well, what are the possible solutions that you can find that you can try and put in a particularly geometrically varied solution. One of the things that helped was the fact that we had to deal with German construction code. It tells you that in each floor, the banister height has to be 1,200 millimeters high, wherever you're going, regardless of the staircase. And of course, if you think of the geometric principle of shear, you can actually overcome, so you maintain a constant height no matter what the shear angle is in a triangle. So we said, that's great, let's do that. And came up with this piece, which is slightly at an angle, sort of to give it, as you'll see in a minute, some sort of accentuation around the corners. This is this big sort of piece that we call the sword. These are variable geometry, flexible, sort of twisting components. And up here is the handrail. And basically, you could sort of assemble that so that with this component here, you could pretty much meet any inclination. And you can see because of this angled distribution of these rods, you're actually getting this sort of inverse pyramid effect around the ends that allows you to look down the stairs. So that's the solution, basically. They make these, there were 46 of these, and they were sort of all identical. They were laser cut out of 10 mil steel plate. And they were also laser surveyed into site. They threaded the 10 mil rod, capped the ends, and bolted on the handrail, and they did the whole stairs in 2 days, but basically out of a common set of components. And the contractor who eventually did it, we went to about 10 different stair fabricators, and all of them refused to do it. They said, we don't think this is ever going to work. The geometry behind this, particularly this sort of inverted pyramid thing, we don't want to get into it, And the only person who did was a company called Musik, who did a lot of pianos work, and they sort of understood what it meant to work in the computer and actually use the computer model as a way to build this. And that's sort of the result. And to me, the nice thing was that it was actually applying some sort of new design ideas to a problem that we have a lot here in Europe, which is we have to deal with a lot of existing building infrastructure. In LA, it's all tabula rasa. I get to do whatever I want. Here, you do have to interface with the existing stuff in some form. If you expand that to a broader level, this is back to Frank. This is the MIT Data Center. The question here is, if you want to build a facade like this, you say, well, that kind of looks easy. It's sort of not a curvy thing. It's sort of straight. Well, in fact, it's not, because these windows are all distributed at weird locations. And you really do have to break down the facade into an assemblable set of components. In this case, dictated, of course, the dimension by transportability, both on a truck and how you can wheel these things on a site so the crane doesn't crash into everything, and figure out how you're going to put these together. And if you look at them, they're all different, right? You can say, well, they kind of look similar, yes, but they're actually all really a little bit different. Maybe one or two are the same. Some are longer, thinner, shorter, wider. So you're talking about, in each of these pieces of facade, you have about 120 different panels. We had about 7 of these facades wrapping around the building. You do the math. If you have to get some people to detail them at the contractor to do all the shop drawings and the shop tickets, basically you can't pay for it, right? Basically, you're not going to be able to design this way. So what helped us was the kind of computation, the computer tools, the parametrics of the CATIA. In this case, where, going back to sort of talking about nature again, you can talk about having a seed. In this case, we're talking about 4 different seeds. This is sort of, application of that sort of thinking to this thing. Different abstract type, different seeds. One is just a panel. One is a panel with a window, corner conditions, with which you can describe about 90% of those panels. You're still going to get the oddball thing, which you have to do by hand, but that's the way the cookie crumbles, as it were. And you sort of start with an abstract type, that you actually instantiate and map to vertex coordinates that you survey off the model, and the system then actually generates the particular instance, if you like, the individual of a population of all possible components that can be described by the system. So basically you have a topological commonality along a family of geometric individual components, and these come out fully detailed, obviously, and again, going back to Airbus, you can obviously manufacture directly from this, so you come up with a sort of a process where the components are being produced off the model into a database, instantiated, and actually producing your bill of materials. You know what the cost is going to be, the amount of time, the shop tickets that the fabricator is going to need. We'll talk about sequencing and barcoding in a different project, but suffice to say, again, you control the project process. These you then take on site. The model, in fact, is used on site. So basically, this initial idea that I was generating some form on the computer and I was working through design, to be able to maintain that mastery of the process, being in control of that process all the way through, is something that you want to be able to do by taking it literally through all the way to the project building site. In this case, we have, you can see a reciprocity between the two. This is the instrument of contract. This is a contractually binding master model that you build off of, not the drawings. And we're basically using laser total station to survey specific cardinal registration points on the site to plot our steel, or maybe to survey in place when we pour the slabs. We're going to pour in the geometry clips inside them to control the panels. And at the same time, we can use a Cyrix scanner, which is a giant building-sized point cloud scanner that can actually bring back into the original model a three-dimensional snapshot of what's been built that day. We did that every day. And you bring it back into the model, and you can see, is there any deviation from the tolerance? In the sense, you know, if there are any mistakes, do those have to be rectified? Who made the mistake? You can obviously tell that immediately in the contract document. So the panels go up, they get bolted into place, and then, it being Gehry, they get covered by steel skin, so you don't see these nice panels anymore, but if you peel it away, that's what you find. This is kind of maybe slightly more mundane project, but nonetheless important. This is now at the other end of the spectrum. This is also a non-Frank project. It's a big tower in Hong Kong, 70 stories high. It's a complete concrete frame tower that is being done by a large developer there called Swire. And Swire is one of the original Taipans, which are the original British or colonial, trading companies in the 19th century. So they moved from doing just trading and shipping to manufacturing in China. If you buy a Coke can, it says Swire on it. They own Cathay Pacific Airways. So they really understand as a client what it means to work with efficiency. And they really understood the usage of tools like this. In this case, not a particularly complicated design. But they wanted to save money and expedite the time. To them, time to market for an office building like this is everything. And the ability to deliver this to the marketplace is crucial. So they wanted to speed up the time and also save about 10% of construction cost. So saving 10% of construction cost on a project like this, which is about 450 million US dollars, is a significant amount of money that is worth a bit of time and research to find out is a better way of integrating a process that is already a very fast process. In this particular case, in China, for those of you who have worked in China, you may know that you do the fast track of the fast track. In this case, it means that you're actually still designing while you're already building the building. So it's like guerrilla architecture, and you're beginning to dig the foundation and pour the rafts and put in the caissons and the piles when you don't even know what the rest of the building looks like, and you just hope it's going to work. And Swire is so methodical about how they do this. It's actually stories that they have actually ripped out part of buildings they already built because they decided they wanted to look different, just to capture the exact market perception. So this is really very real stuff, right? I mean, this is guys driving the steel down into the ground, and this thing is moving at full pace, and you've got to work quickly to catch up or even stay at pace because they're just going to put something up, doesn't matter what. It's true. I mean, it's pretty hardcore. So in this case, it's about collaboration. It's about how can you create efficiency and a dynamic about interchanging that information. Here's our friend, this central model that we've been talking about. And in this case, it's really about how do people interoperate with this. And at this point, it's all about the human level. It's all about how people engage information and how about particularly the politics of getting people to buy into this. Everybody has their own weed. Everybody has their own risk, adversity, and so on, or aversion. But to get literally, on the one hand, you have the design team with the project managers and architects adding into the model. You have a figure who coordinates this entire thing at the same time, asynchronously, may I add, with all the different consultants, and at the same time, a very, very smart and savvy client like Swire who's constantly looking at what the hell you're doing and trying to work very, very fast. The point about asynchronicity is that, of course, as you're undertaking different design and detailing operations, people work at different speeds. They are updating information at different speeds. So this idea that, you work on a shared virtual model where things change in front of your eyes doesn't really exist. The system does have to be able to cater for people working within the context of their own job scope. So this, to me, in a way, is almost like the most important slide, right? This is really all about the people who are present in this constellation. It's almost like 40 people here, if not more. And all of these have to somehow buy into this and actually participate and produce solutions that work within the system. And everybody, as I said, has their own risk adversity, has their own idea about how this should work. The client has this e-services team here, which is basically a very smart ninja group that kind of wants to make these buildings in a very effective way. And the only way that you can sort of arrange that is by having a very short leash. And by that I mean that you have, basically, the client has very, very direct contracts with each one of these consultants. It's not like you hire the contractor and then you novate the consultants to him. He's actually hiring them all directly and getting them all to toe the party line directly. And they said, well, what's the best way of working? And they have been working now for a number of years trying to get people to collaborate. And so what they did is they basically rented an office in this Taiku place, and everybody sat in there. They've been sitting in there now for basically a year already. All these people working from the different team members, where we basically, in this case, not as a design collaborating architect the way that we do with Frank and a few other architects, but in this case really as a facilitator of process, got them to work together off a single three-dimensional model using an online information system to exchange information and actually execute the project. So in a way you become almost like another consultant in this case to actually keep the entire process going, if you like, a kind of a glue between all the cogs. And this allows, of course, the contractor to directly out of that model tender out the specific subcontracts that he wants to have control over financially. Again, very hands-on contractor, tendering out the elevators, the glazing and the mechanical systems. And then later on, novating them to a general contractor. But the interesting thing here is that these were tendered out before the general contract was awarded. So the general contractor then has to make do with these guys because that's who the client wants. So just a few images out of that. It is in a rendering model. You could take this and stick this in a rendering package and make it look pretty. In this case, it really is a construction document. In this case, looking at the structure, as you peel away the slabs, the core, the mega columns, you have 8 mega columns around the perimeter, the structural core itself with these sort of bracing systems. At 2 locations, these outriggers up the tower that are used to brace the buildings, and you have events of typhoon, you have a lot of building movement. All of this is actually an accurate representation of what you're actually going to build. And the thing gets more complex and even more useful when you start talking about project coordination. And for those of you who have been in practice and have had to coordinate projects, you know that the mechanical engineer will do what's called a CSB, a combined systems drawing. And the combined systems drawings basically look at integrating all the different mechanical systems, ventilation, plumbing, fire safety, electrical, and so on. And those never work, right? In most cases, they never really work. And you sort of goop these things and kludge them on site in some form. And as I said before, in a particularly complex project, it just won't work. In this one, it's just a lot of wastage. And that's the money that the client is trying to save. And what we found, that these tools that we use allows us to capture pretty much every single miscoordination clash. And what's interesting when you're looking at all these things wrapping around each other, not only did we find that there were a lot of clashes, but over half the clashes was within that one consultant, i.e. the mechanical guy clashing with himself, right? So his HVAC department would crash with his plumbing department. It's like crazy, right? And so they spent most of their time just sorting out their own mechanical systems before coordinating with structure and finishes and so on. But also begins to serve as a kind of information database. And that means that when you integrate everything, here you're going up from the basement, you have the ramps here, you see here you have the different equipment rooms and the different risers and the ducts coming up through the building. that point also the structure comes in here, the framing beams and the slabs. And you keep going up, and the project begins to come together as you're taking up also the mechanical systems through the floor. On each floor, obviously fully detailed with every single ventilation duct and diffuser and lighting box, and then it begins to get kind of crazy, right? And you think, wow, this is really mad. And in fact, whether you like it or not, that's the fact of what you're building. You just never get to see it this way. And this is sort of every single fitting and fixture on this project. And it's even more crazy because now you got them coming up through the basement. This is like one of those anatomical models, I'm sure you've seen them, where they take a dead person and they pump him full of resin, and you're left with this really weird red resin tree of the guy's blood system. It's really disgusting, but anyway, it kind of looks like that. And they get really, really, really crazy like this, and at that point you see really where the need is, because here we can see we have these diagonal brace frames, these outriggers, and the outriggers, if you saw them in plan, they're not just coming off square, they're also coming off at an angle. So this thing is really kind of going diagonally through space. And what we have here is basically this piece here winding around this diagonal piece, this diagonal beam here. And there is, given the tightness and the amount of equipment happening in that mechanical floor, there really is no other way to wind this thing around. So being able to actually coordinate there is very important. You can do lots of other things, obviously, out of that model. You can produce drawings, you can analyze it, query it in terms of producing logical representations of the building. Show me all the, all the structural shear walls that are of a particular type of concrete mix. But also the idea that when you do a sort of financial analysis or material quantity analysis of the building, you're actually getting what is basically a different kind of view onto the same project. You could argue that this particular three-dimensional view of the project and this numeric view of the project are almost the same thing. They're just different takes on the same thing, but they're coming from a single data source that coordinates all that information. So now it's no longer just a design tool, it's not just a coordination tool, it's actually now a financial control tool as well. So you see now the advantage of investing the time in something like this, because it just gives you that by much better information that in the end, working with your client, you know as an architect how much this thing is going to cost. Again, parametrically connected, I make a change, I can see whatever my glazing is going to cost. And you can also use it to count your toilets. In this case, the guys wanted to have every single toilet in there, so you have like 1,296 loos and 658 urinals, and you just count them all. Another non-Frank project, you may know this one, in Beijing, the Olympic Stadium, Herzog and de Meuron. This was a project where Arup asked us to help them out. In this case was about really kind of defining and understanding what the geometry of this project really was about, in particular in the context of actually getting this thing built, i.e. fabricated, and sort of the processes that went with that. The project, for those of you who know it, is actually not a chaotic project. There's actually sort of some method to the madness, in the sense that you actually have it's a very large, very round ellipse, but it is nonetheless an ellipse. You have these 24 gables that sort of reside around the perimeter of the project, out of which you sort of lay tangents to this interior oval. You take the bisectors of those tangents to draw another line, and that's how you get this sort of thing. So in fact, the stadium is actually rotationally symmetrical, meaning that this side is exactly the same as that side, and at least you get a number of 2 for every component that you want to build. And so the problem there was really sitting with the teams, in this case in Beijing, as well as in England, to figure out the different issues that were coming up. And a lot of it was really about design exploration, because there was a design intent that was mandated by the design team that wasn't really fully resolved unless you explore this in a lot of detail. In this case, it would yield a lot of these really weird sort of spontaneous Chinese conversations where you would have this moment of discovery where they would discover a specific aspect to the design that you hadn't realized yet, because you just have a sort of a relatively simple model in Rhino or on paper or something, and as you actually start trying to put components together that build this thing, you realize, oh my God, this thing is going to go this or that way. What does it mean for the weld joint? What does it mean for rolling the steel, and so on? So you really did spend a lot of time exploring that. The sides of the building are an irregular conical extrusion of that ellipse, meaning that they extrude at different angles that vary through the sides. So how do you actually place a staircase that wraps itself around that? What is the implication of that together with the way that those guys want to detail it? And so that's sort of the outcome of this, is actually this sort of stepping stair that is in tangent to the curve here, but actually every time you have a landing, it does a little step backwards. So you got this kind of sort of zigzagging stair. And that, again, if you like, is actually dare I say it, an emergent result of that underlying geometric set of rules that were placed on the projects, and this is sort of the exterior you're going to need to fulfill it. Also to fulfill, of course, the Chinese construction code. And on the roof, then what you get is this sort of Pink Floyd imagery where you have these components flying in space. Basically, these are self-similar components, again, not unlike the MIT cladding systems that we looked at, in which case here they're coming off a common template, one of these smart templates, which is basically like, if you know an AutoCAD block, it's a smart adaptable block that will reconfigure itself to a particular set of geometric conditions. And with that one piece, you can basically detail all your joints in the roof. And then comes the problem. The problem is that, again, you have to think, never mind the software, you have to think as an architect here, or in this case almost as a structural engineer, which is these joints are, the plates on the top and on the bottom are flat. They're flat pieces of steel plate. They vary anywhere between 40 and 130 millimeters thick, depending on the torsion that they're getting, but the joints are actually flat. And so that they're laid, this is on that surface on the roof of the whole stadium, they're laid as tangents to that surface through that specific point. There's a point, there's a point. What that means is that as the surface is twisting, this surface, this plane here and this plane are not coplanar, right? Which means that they're actually twisting out of the plane to one another. That immediately means that if you're going to have tangential joints, you're going to have a torsion in the beam. And torsion in the beam is very, very complex to achieve when you're double curving a steel box girder like that weighs 18 tons and is 50 millimeters thick. So you say, well, how about we don't have a torsion? What about if we just have curved in one direction so that this side is flat, the other side is flat, and it just kind of goes like that? And that's how you get this purple and this pink. They're actually two beams, one on top of another, and they're very slightly similar but warping one on top of another, because one is looking to have the torsion and get a better joint, and one is kind of not having the torsion, and you're going to get a tiny little jump to compensate for that lack of coplanarity. You could say, who cares? It's 60 meters up in the air, nobody's going to see it. But the problem is you're going to get very bad weld joints, you're going to expose yourself to steel corrosion. And so those are decisions that have to be made by the design team that affect, on one hand, the outcome of the project, but also the manufacturing process. So as you unwrap this thing, in this case, it's not like the developable surface before. This is like the inverse of a banana. You know that when you peel a banana and you put the banana peel, you can try this at home, right? You can put the banana peel on the table and it's curvy and you can't really mush it down flat because it has a curvature to it. By the same token, there's a curvature here, but I'm going to build it out of flat steel plate that's coming off a rolled plate mill, and that I'm going to laser out into the shape, and then it's going to be bent and curved into this form, and actually then welded together. That means that while you're going through that curving, there is a deformation going on, and that deformation means that it's a deviation from the actual design intent. You might get some buckling, you might get some warping, or you might have to really curve roll the steel, maybe cold roll it, warm roll it. There's a further deformation going on when you actually weld this stuff through the heating process. So mapping from that to that in real material world terms is not so easy, nor is it to track it. You know, you want to actually be able, in this case for the contractor and the client, to track down every single individual plate that makes every single individual girder that makes every single one of these components. Because if there's any problems going on with the quality of the manufacturing here, maybe that there's some bubble in the steel and it's, you know, it's rusting or something, who is responsible for changing that? Which of the 7 steel mills did that? So you come up with a sort of universal identifier system that is like a fractal numbering system, sorry. You can see the jet lag kicking in now. I'm going to start mumbling soon. And that goes from the layer of the individual plate to the component, which is an aggregation of plates, to the assemblage of frames into this overall piece, so that you can argue that there is a reciprocity between pre-construction at all the different levels of operation with the actual construction process itself, meaning that you're lasering out plates, you're bending them, welding them together, and assembling them. The caveat here, of course, is that you're working with Chinese contractors in the People's Republic of China, and there they have the cheapest commodity there is human labor. And they say, well, why are we going to invest in all this stuff? We don't understand it. We're just going to have people do it by hand. So they're going to sort of read coordinate points along these curves, make a wooden jig, and get 20 guys with big giant hammers to whack these things into place. And that with the deformation and so on, is kind of scary because of the quality control problems. I had many meetings in Beijing trying to argue the point of going this way. So far, it hasn't happened, and one of the Arab directors rang me up and said, look, I don't think you've seen the last of this yet. They're going to come back screaming in a year because they realize they can't do it. The even scarier thing is that this stadium is actually going to be carved up into 4 pieces, and 4 different corners are going to be awarded to 4 different general contractors. And you're going to hope that at the joint, the seam, or one is going to be faster, so you're going to have a bit of stadium, half-built stadium, no stadium, It's going to be a cool design. So, there's a whole other aspect that you can be sort of fascinated by geometry like this. Personally, I do a lot of design work on my own, and also, with Frank and other people that allows me to experiment in a lot of formal design. But you're constantly being reminded of what does it mean to get something like this built, right? And the building of something like this really has to be the goal for I think, what you're trying to do. I'm going to go a little bit quicker through some of these other projects. This is a little bit about scripting. Some of you guys, I think, are interested in scripting, or what does it mean to control a design through a script. This is a project in Chicago. It's a curvy bridge by Frank. In this case, it was about actually generating these patterns that are patterns of panels that you clad this bridge in. In this case, it's about making the panels actually fit so that they don't waterlog, they can be disassembled when required, and so on. So again, you're unwrapping these surfaces. In this case, then defining a program, a computer program, that's actually going to walk around these surfaces and lay out these panels by having the seams being lines that are basically normal to the tangent of that curve at a specific point. And I got a question trying to find a sort of level of panel commonality. So at some point there's a straight line happening here, which is basically the Euclidean bisector of an arc, meaning that you're not actually calculating curve length along the curve, but actually along 2 points along a curve that are defined by a straight line. And so this thing creeps around and lays out these panels. You can then wrap them back onto the surface like that, and this is what you get. And you get this kind of nice sort of fish scale texture. You get here a little bit of sort of kind of armadillo-like quality. You can see here that straight line, which is something that the design team was looking for. So it doesn't just only read as a fluid curve, but it does have some sort of tectonic quality to it as this thing wraps around. And you can now go and walk around it in Chicago. It's pretty nice. A lot of people skateboard on this like crazy. It's really weird. Another such project is this is another Frank project that is about glazing, and this is an atrium system. It's about 60 meters long, and at its widest point, it's nearly 30 meters wide, and it's completely free-form shape. And again, in the office, it gets designed through these models. The piece on the left is going to be made of anodized sheet metal, and therefore you can argue that designing it out of strips of paper, putting it together, you're actually already looking at how these computerized developable shapes are actually going to be built, because these are going to be the seams of these metal sheets. Not so over here, because you're not obviously, even if you had an infinite amount of money, glazing technology is not far enough along that you can have a 60-meter long strip of glass like you're using this acetate here. So you have to obviously find a way of rationalizing it and figuring out a way to build it in some sort of panelized way. And this goes back to that very first project I showed you about the quadrilateral panelization systems, which means that basically you're trying to find a solution that is constructible at a given cost and placing it onto this sort of free-form surface model that's coming off that physical model, this sort of digitized shape. And of course, you can go through a whole laundry list of possible construction methods. You could, again, mill it out and sump the glass, and you can have a bunch of sumped shapes of curve. There's a huge range of triangular tessellation algorithms that look at how you can break down a surface into triangles, or you can find something that's a bit more regular and actually kind of simplifying the design by using something that has 4 sides and not triangles. particularly the problem with triangles. That first project I showed you, which was the DG Bank in Berlin, has a very, very high amount of complexity. It's very, very expensive. You have many, many mullions. It's kind of like the British Museum down the road. You have very complex node joints, these six-pointed stars, and kind of being able to implement that is a very, very expensive process. And we were using for this new project the same structural engineer, which is Schleich Bergermann partner, who's an ex-Frei Otto collaborator in Stuttgart, who really helped us understand this project, but also this new one, in which we had developed, through this particular job, a series of metrics that allowed us to gauge what it would take to do something like that. So we made a first model in the computer of a triangulated surface like that. We did a cost-based analysis through the computer. We basically immediately found you're not going to fit this in the budget. It was over the budget by, I don't know, 30, 40%, 50%. So you've got a big problem there. At that point, you're going to say, I'm either going to throw this design away. I'm not going to have glazing at all. I'm going to just make it a big vault, like a cylinder. I'm going to find something else to put this thing together. And so we worked with Schleich to capture some ideas that they've been developing on. We ended up writing even some scientific papers on this. I won't really go into the math of it. So suffice to say that these are what are called scaled translation surfaces, which means that by governing a certain number of control splines, you can actually get these surfaces that approximate any freeform surface as opposed to being a torus patch or something more regular like that. And you're always getting these four-sided flat pieces of glass, these sort of quadrilateral panes, which now you could cost again. And suddenly, basically, what is the advantage of this system? Well, you've eliminated a third of the mullions. You've gotten rid of these diagonal pieces. You've greatly simplified the node joint, which is expensive. But also importantly, you have eliminated these triangular corners, which leads to a lot of sharding of glass. It's very high amount of wastage in the factory. And you can now rerun that based on previous jobs they did and say, how much would that cost? And of course, we were lucky and that came in within the budget. So basically, you program in the computer something like a smart bubble gum. Here's your design surface. Now you can take this thing, you could almost design with it if you wanted to, and you start tweaking, pushing, pulling, knowing that every time, just like that sheet metal tool, is going to give you these quadrilateral four-sided components. And you can almost say that this becomes like a guide image, again, going to that idea of the blurring and the sort of this Heisenberg idea of unpredictability or lack of precision, dare I say, that is inherent to, in this case, a design process. Ultimately, that becomes sort of the design rationale. In this case, we used a number of, again, going back to the aspect of nature, we employed something called you may have heard about genetic algorithms. In this case, we used it to actually optimize and generate the ideal surface based on that construction system that would match the idealized blue shape. This is one half of that piece that carries on up here. And the yellow shape is basically a surface that has that logic of the quadrilateral planes built in. And you're getting the computer to evolve the optimal solution. So you're converging here onto the right shape. You're doing a tracking of the distance from the original design shape to the one you want to the moving, evolving quadrilateral glazing one. You can then, once you got it, you can trim it out. You can do the same thing for the node joints that you did, for example, with those MIT panels. In this case, again, you have butt joints where you either have a weld, you have diagonal tension cables that brace each one of these panels, and each one of these is going to be individually machined. So again, to detail all of these are 8,000 different nodes. Would take an inane amount of time. You're not using a ball joint, a kind of a Miro joint, because there's a lot of torsion in there, so we need to have a welded butt joint, mainly because this is a free-form surface and not a structural surface. Or rather, it does perform structurally, but does have to take up a lot of torsion between these members. So then the script basically runs through and can place each one of these in detail, all 8,000 of them for you. And so this is the result. On the left-hand side is that design model, and the right-hand side is now the constructible solution. And this is, again, important because it's basically enacting a specific design theme, but with the rationale of what is basically buildable in that project, and also within the budget that is available. Here's another one you can see here, actually, and this is the final model. You can see all the little squares here, and they sort of etched the diagonals into that. And that's kind of the actual shape you would build. So it goes back to the question, where is that original design? Is it this one? Is it this one? Is it some sort of, if you talk to Craig, he'll talk to you about a dream image. It might be, it might not be an image at all. It might be a computer algorithm that generated the shape, right? But somewhere, at some point, you kind of converge on what is actually the solution that you're going to put together. So it becomes like a steps, a sequence of different components that you are ultimately coming up with a final solution that not only embodies that shape, but works structurally with the supports. It has this kind of constructability map to it. It works for drainage. It works for bomb proofing and all these kind of things. You can try the same thing. This is a different project. This one has like an armadillo-like skin, but similar set of ideas. In this case, it's about these overlapping pieces where, again, you have components that, in some cases, you have these, two of these are always the same. In this case, we had a set of rules about how much overlap there can be between the different components, and basically capturing them in the computer and analyzing, again, where, as you're designing parametrically in the computer, you are actually trying to find what is the solution that can be enacted with this particular detail. In this case, you can have a maximum of a minimum of 60 degrees of angles here. If it gets any smaller, then again, this thing highlights in red. You've got a problem. You've got to move these things around so they all work. And again, the gratification of that is to seeing that go up. This is a full-scale mock-up of a whole bunch of these panels in our parking lot in LA. So we work inside this big shed here. And you can actually see how this thing is coming basically together, that the gaps actually work, that the ventilation can work through that, and so on. This is a building that was supposed to be a sort of self-ventilating green building. And so this kind of goes back to this idea, again, of being, you know, an architect that can empower himself. You guys can work with tools that you can sort of influence how you use them in the downstream. So I think I'm going to conclude there. I hope this gives you an idea what it means to really trying to push the technology, but to also support it as a design process. Obviously, if you're designing directly in the computer, you can potentially drive that process in an even more sophisticated way. Certainly for us, the small victory is that ultimately the design does happen in the computer, because those initial shapes do get rationalized and formed in the machine. So with that, thanks for listening, and thanks for waiting.
Chris will take a few questions.
Yes, ma'am. Good question. Mostly it's Jim Glimpf pounding his... how do you get clients to buy into this way of working? Mostly it's Jim Glimpf pounding his fist on the table. Or Frank saying, if you want to work with me, that's what you got to do. In most cases, you can actually prove or demonstrate that there's a particular process of enabling of particular designs that wouldn't be possible to do otherwise, or that would perhaps be much, much more costly or more complex to do if you didn't have such a process. So in some cases it sells itself, but it's not really about selling here. It's really about achieving a project, and you can have a dialogue with your client and also with the rest of the team about what is the right way to go about this. And in some cases this is a solution, some cases you don't need it. You know, you can actually sort of just kind of group it by hand, or try and derive two-dimensional drawings and build with that. One way of doing a lot of these complex shapes is that I build the shape and then I sort of slice it and I make all these ribs and then sort of make my stuff between the ribs. That's not always very economical, because the ribs are very, very difficult to join together, so you end up spending a lot of money on the joints. And so you actually want to have in the design sense, a tabula rasa, you say basically we're open to all solutions and we want to find a way to explore them. And what is a good way to explore them? You know, you saw the image of the CD-ROMs, right? I mean, that's like really low tech. So the computer doesn't always help to sort of serve as a bridge, in German the Eselsbrücke, to finding a potential way of working. But it does help you to record that. You guys are as jet lagged as I am, but Yes, sir.
When it comes to engineering one of those projects, if the engineering office wouldn't have CATIA or the tools that you are using, how would you deal with that thing?
Well, I think the important thing is to realize that it's not about the tools, it's about the process, right? It's about the intent. So you could say, could you do it with Revit? Yeah, maybe, smart geometry, custom objects, whatever you want to use. The point is, do you understand that how you, for example, capture information in such a way that if I'm the architect and you're the engineer, right, and I need to give you something to analyze, how do I know that if I give you a model and I translate it from me to you, that the model that I give you is the same when you get it? There is a translation and interoperability of data process going on. How do you record that so that there are minor variances that go on, for example, in the representation of NURB surfaces between different softwares. It's about interpretation and code, whoever wrote the code of the NURBS, So you actually have to define very clearly what, you go and say, what information do you really need to do your job, right? And thereby you can define, okay, what are the tools that I'm going to need, and what is the process that governs that? Now, if you have a common set of tools, obviously you are doing a lot better because you're avoiding a problem of translation of data. And of those of you, I don't know how many of you are still studying and how many of you are working or have worked in offices, you'll probably know that translating files is like everybody's thorn in the side. Whereas, well, my software doesn't save that format, and so you can't read it, or I'm going to have to save it into Rhino, and then you open it there, and you've translated 5 times over, and it falls apart into triangles, and it's horrible. So it's true. It is part of the pain, and at that point, say you're not just painful that you have to sort of reassemble this data. There's actually a risk associated with that because you're reinterpreting imperfect data. And that point, when you're doing structural engineering, it's a very, very big problem and a big risk. That's why in the olden days and even today, most engineers will say, "Listen, it's great that you're doing 3D. Looks great. We don't want it. Just give me the drawings. I'll rebuild my own model in Robot or in SAP 2000 or Nastran or whatever I'm using." And then I'll do my calcs, and then I'll tell you what the values are, and then you can do something with it, which is obviously takes a lot of time.
So in that case, who's responsible about the manufacturing drawing? Is it the engineer or the architect?
No, you're talking about shop drawings?
Yeah, about the
Which drawings are you talking about?
But not the drawings, maybe the model or the surface, like the final surface.
But again, is it at the shop drawing level, or is it at the construction document level?
What if the construction drawings are a model?
Well, the model is an evolving thing. You see, we talk about construction documents and job drawings to kind of compartmentalize phases of a project. In the end, if everybody has worked in that way, the final model that exists, because you take it through the construction process and the contractor is still updating the model, you actually have basically an as-built model of the building. So who actually modifies that model happens at very specific stages. In the example of the concert hall and the glazing, or the cladding, right, the shop drawings of the components that hold that thing up are done by the fabricator. But the actual layout drawings of the surface and how that has to be panelized is done by the architect. Right? So what I'm hoping this talk gives you, besides keeping you from your dinner, and I'm sorry about that, but I was locked away, so maybe it would have been better if I stayed locked away. But as I hope that you see that this whole thing does go back to architecture. I mean, I practice as one, and I think we all do. The point is, it's about if you really have an interest in really pushing a design language and a design exploration on every level, you think, what are the things that will help me as an architect empower myself to execute the projects the way I really want to do them? Because you're going to find at every turn that there's a client who wants to shave off the budget, he wants to lower the risk, the contractor doesn't want to do it, crooked walls become straight, and so on and so forth. How do you really maintain control and convincing control in that kind of master builder role? I think that's sort of the underlying theme of this talk, is really about, as you get more and more into practice, I guess most of us fantasize, me included, about, maybe one day you have your own office. What would you really need to do if you have a design idea to really transact it in the way that you really want to do it, and not that you get run over, bulldozed by some client, right? And if you have a technique or a method or tools, process, again, you can buy the best tools in the world. You can buy CATIA. It's not going to help you if you don't really know what are the implications behind it,